let's talk about molecular orbital theory. So this one's a little more complex. So, but it's actually it's one of the things that looks very daunting, but it's not as hard as it looks. If that makes sense. Well, you'll see. So, first things first, we need to talk about what is molecular orbital theory. So, molecular orbital theory basically says, all right, let's think about our orbitals as waves. Okay? So, when you have waves, you can combine waves, you can add waves together. And when you add waves together, you add them either constructively or destructively. So, we have a wave here. Okay? And we had that wave lined up the same, right? So, if I add those together, then I get basically double the amplitude, right? But if I subtract those wave functions, okay, they go destructive, right? So that's basically the idea here. So if my wave functions add constructively, okay, I make what's called a bonding orbital. And if they add destructively, then they form what's called an anti-bonding orbital. And the anti-bonding orbital will have a node. So basically what happens is your s orbitals and your p orbitals combine to form bonding and anti-bonding orbitals, and from that you basically fill up the electrons from each element, and you can see basically the electron configuration for the whole thing. What's nice about it is that it shows magnetism and bond order, which is something that Lewis structure or molecular like VSEPR doesn't show you. So it gives you more information. The only problem is if you're not doing it for two atoms, diatoms, then it gets really complicated really fast. So it's really only practically useful for two atoms together. So let's look at how it works. Okay, so you see this chart here, and we start with laying out. Okay, so for instance, this is fluorine. So we lay out the atomic orbitals. So we got our 2s, and we have our 3 2p's. So these are degenerate, so they go on the same level. We do the same thing for the fluorine on the other side. Okay? Then each two orbitals combine to form one constructive and one destructive orbital. So this is called sigma 2s, that's the bonding. Then sigma star 2s, that's the anti-bonding. Then the p orbitals will combine to form a sigma bonding and anti-bonding, and 2 pi bonding and anti-bonding. Now, the pi bonding are above the sigma bonding, but the pi antibonding are below the sigma antibonding, as you can see here. Okay? And so then all you do is you just take the electrons on both sides and fill them in, and you follow the rules. Hund's rule, right? We fill up the lowest. No, that's not Hund's rule. Hund's rule is spin up first, then pair with spin down. Aufbau principle, start at the bottom and fill our way up. Pauli exclusion, only 2 electrons per orbital, in this case per line. Okay? If you have unpaired electrons, then the molecule is paramagnetic. Otherwise, the molecule is diamagnetic. And then you can calculate the bond order, and it's the number of electrons in bonding orbitals minus the number of electrons in anti-bonding orbitals divided by 2. Okay? So, if we look at fluorine, okay? So we've got 2 electrons here, 2 electrons here, 4 total, 1, 2, 3, 4. We've got 5 and 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's filled up, right? So we see there are no unpaired electrons. So this is diamagnetic. And the bond order for fluorine would be the number of electrons in bonding orbitals, 2, 4, 6, 8, minus the number of electrons in antibonding orbitals, 2, 4, 6, divided by 2, or 1, which correlates with what we know of fluorine is a fluorine-fluorine single bond. Okay? Let's look at oxygen. Again, you do the same thing. Fill up the electrons, fill them up, and then we say, okay, we have unpaired electrons here. So oxygen is paramagnetic, meaning it's attracted to a magnetic field. And then if we calculate the bonding order for oxygen, okay, we see that it's bonding electrons 2, 4, 6, 8 minus antibonding 2, 4 over 2, or 2, which correlates with what we know, the oxygen-oxygen double bond. There you go. That's all it is. It's not that complicated. Now, you might see for like boron, carbon, and nitrogen that the pi 2p bonding and the sigma 2p antibonding are switched. I wouldn't worry about that too much. Okay, so let's do a practice example. So let's do carbon monoxide. Okay, so we're going to put carbon on this side, and we're going to put oxygen on this side. You'll notice we're starting with 2s because that's where the valence is. The non-valence does not matter. We're ignoring that. So the valence is on level 2. So we're starting with that. Okay, so carbon has 4 valence electrons, right? 1, 2, 3, 4. Oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. Okay, so I've got 4 electrons for my 2s. So 1, 2, 3, 4, and I've got 2, 4, 6 electrons for my 2p's. So 1, 2, 3, 4, 5, 6. There you go. So it is diamagnetic, and the bond order for carbon monoxide is going to be number of electrons in bonding orbitals, 2, 4, 6, 8, minus electrons in antibonding, 2 over 2, or 3. And if you were to draw the Lewis structure, you would find that it is indeed a carbon-oxygen triple bond. So some mistakes I see frequently is that people, the electrons on both sides, you're just writing this out so you keep track of them. You just add these together, and it doesn't matter which side they're coming from. Okay, so I have 6 total, so I just go until I have 6. Okay. The other thing I see is people will do like, oh, but 1, 2, 3, 4. No, okay. You have to have 2 electrons in the lower orbital before you move to the next one. Okay, 2 here, then I move 2 here, then I move 1, 2, 3, 4 here before I move up to here, before I move up to there. Okay, so you have to follow the alpha principle or you will get the wrong answer. But it's one of those things that looks complicated, but it's really not as bad as it looks.